The next one is the crevice corrosion. So crevice corrosion is very similar to pitting corrosion. It basically involves the movement of species from a place where we have an aeration plus, so we have too much oxygen, to a place where we are depleted in oxygen. We see here that, for example, if we have a crevice former, wherever it is, it could be a bolt tie there, and then we form like in this example there. At this edge, at the edge, we have an excess of air, an excess of water, an excess of oxygen. So oxygen plus water made this OH plus, OH minus, 4 OH minus. It means we need to have 4 electrons to be balanced. So we need to have iron twice, so to have the iron 2 plus. This is built. This OH is taking this iron 2 plus and keeps building, but then it's still depleting. It's still depleting. The corrosion is going inside there, and it's happening very, very aggressively. It's moving very fast. There is a typical example. If you put water in one scissor, if you have scissors to cut, and you put a drop of water in those and you close it and you leave it there for a while, you will have the crevice corrosion. It will be this is an aerial cell type in which the oxygen is reaching that place and is corroding locally there. So this is a very typical type of corrosion, and is very damaging type of corrosion. Next one is galvanic corrosion. So we saw the galvanic corrosion when we study the sacrificial anodes. So galvanic corrosion refers to corrosion where we have a more noble with a less noble material. So the less noble will corrode fast. And there's a typical example in pipelines, for example, or in any type of engineering design. If we have 2 materials connected by a flange, and this is the example there. So we have one flange, this is stainless steel, and the other is carbon steel. The corrosion, as it's in this, the corrosion will show that the carbon steel at the vicinity, or when it touches the carbon steel with the stainless steel, the carbon will corrode very fast, increasing there, and then goes slow, goes to normal corrosion rate, and the stainless steel will be protected, and then reach the typical corrosion rate. This is the series of galvanic series. So for example, we have the 316 and we have the carbon steel. That's the example there. This corrosion difference, this voltage difference, is basically the driving. This driving voltage is the one that makes the corrosion happen in the galvanic series. We discuss this when we talk about the sacrificial anodes. One factor that affects galvanic corrosion is the ratio between anode and cathode. Remember, the anode is the one that is on corrosion, the cathode is the one that is not on corrosion. So the anode, if it's very small, needs to provide electrons to protect the cathode that could be very large. We need to have, as we saw in the sacrificial anode exercise, we need to calculate the size by mass to how much we can protect. If the anode is big, then it will protect a small piece and it could stand for a long time. If the anode is very small, it will corrode very fast and it will protect nothing. In the example of the galvanic corrosion, when we put together 2 materials, it seems like when the cathode is larger than the anode, so the area to protect, which is the cathode, is larger than the area to corrode, then this is very fast. The corrosion rate is very, very fast and is very accelerated. When the cathode and anode has the same ratio, the corrosion rate is as we explained. In the case where the anode is larger than the cathode, then you have enough material to protect the cathode or to corrode your anode in less in a smaller rate. than in other examples.